To detect heteroscedasticity, we plot the residuals, the differences between actual and predicted values. If they are randomly scattered, we're in good shape. But if they form a pattern, like a funnel shape, where errors grow larger for higher values, it means our model isn't treating all predictions equally. One way to fix this is by transforming the dependent variable. For example, applying a logarithm to house prices instead of using raw values. Another key check is autocorrelation. This is especially important in time series data, where today's stock price, for example, is heavily influenced by yesterday's price. In standard linear regression, we assume that each observation is independent. But if errors are correlated, meaning that past mistakes influence future predictions, our model might not be valid. We detect this by plotting the residuals over time. If we see clear cycles or trends instead of a random spread, we may need a time series model instead of standard regression. Next, we need to check whether the model fits the data well without being overly complex. This is where we use R² and adjusted R². If R² is too low, our model isn't capturing enough of the relationship between variables, meaning we may have left out important features, but if it's too high, especially close to 1, we should be suspicious. A perfect fit often means overfitting, where the model is memorizing the training data rather than learning meaningful patterns. If we suspect overfitting, we can introduce regularization techniques like ridge or lasso regression to simplify the model. Finally, we need to ensure our residuals follow a normal distribution. Many statistical tests in regression assume that the model's errors are normally distributed. If they aren't, it might affect our confidence intervals and p-values, making some variables look more or less important than they really are. To check this, we create a histogram or a QQ plot, quantile plot. If the residuals form a nice bell curve, we're good to go. If not, we may need to transform variables or detect outliers that are throwing off the model. Model diagnostics is like a final inspection before taking a car out on the road. Even if everything seems fine at first glance, we need to check under the hood to ensure everything is running smoothly. Only after verifying these assumptions can we confidently say our regression model is reliable and ready for use. But what if our model isn't quite good enough yet? How do we take it from decent to highly accurate? That's where improving model accuracy comes in, and that's exactly what we're going to explore next. Even after building a regression model and running diagnostics, we often find that it's not as accurate as we'd like. Maybe the predictions are off, or some variables don't seem to contribute much. So how do we take our model from good to great? That's what we'll focus on now, improving model accuracy. One of the most powerful ways to boost accuracy is feature engineering, creating new variables that better capture the relationships in the data. Instead of just using square footage to predict house prices, we might create a new feature like square footage per bedroom, which could provide more useful insights. Similarly, in a sales forecasting model, we could introduce a variable like holiday season sales boost to capture seasonal trends. Well-designed features often make a bigger impact than just adding more data. Another way to improve accuracy is through cross-validation. Instead of just splitting our data into training and test sets once, we can use a technique like k-fold cross-validation. This divides the dataset into multiple parts and trains the model on different combinations of those parts. The benefit? We get a more reliable measure of accuracy by ensuring our model isn't just performing well on one specific split of data. If our model does well across all folds, it's more likely to generalize well to new data. Regularization is another powerful tool, especially when we have too many features. If our model is overfitting, meaning it performs well on training data, but poorly on new data, we can use ridge or lasso regression to simplify it. Ridge regression helps by shrinking coefficients of less important features, while lasso goes even further by setting some coefficients to exactly zero, effectively removing unnecessary variables. If our model has too much noise, regularization forces it to focus only on the most meaningful patterns. We can also improve accuracy by evaluating and improving data quality. A model is only as good as the data it learns from. If we have missing values, outliers, or inconsistent measurements, our predictions will suffer. Cleaning and standardizing data, removing outliers, filling in missing values intelligently, and normalizing numerical features can significantly boost model performance. If some variables have inconsistent units, like height in inches and weight in kilograms, standardizing them ensures the model treats them properly. Sometimes the issue isn't just the model itself, but rather the choice of regression type. If a linear model isn't capturing the full complexity of the data, we might consider polynomial regression for capturing curves or interaction terms for relationships between variables. If our dependent variable has unevenly spread values, transforming it, such as taking the logarithm of house prices instead of using raw values, can make the relationships easier for the model to learn. At the end of the day, improving model accuracy is an iterative process. We build, test, refine, and repeat. The key is to find the right balance, not too simple, not too complex, but just the right level of flexibility to make meaningful, reliable predictions. But while accuracy is important, we also need to think ethically about how we use these models. What happens if our predictions introduce bias? What if they unintentionally discriminate against certain groups? These are critical questions, and that's exactly what we'll discuss next: the ethical considerations in linear regression. Linear regression might seem like a purely mathematical tool, but it has real-world consequences, and that means we need to think carefully about the ethical implications of how we use it. Models don't just predict numbers. They can influence decisions about people's lives, from hiring and loans to medical diagnoses and law enforcement. If we're not careful, we risk introducing bias, violating privacy, or misusing data in ways that cause harm. One of the biggest ethical concerns is bias in predictive modeling. Regression models are trained on historical data, and if that data contains bias, the model will learn and reinforce those biases. For example, if a company historically hired fewer women for leadership roles, a regression model trained on past hiring data might predict that gender is a weak predictor of success, leading to continued discrimination. Similarly, if a bank's loan approval model is trained on biased lending data, it might unfairly deny loans to certain demographic groups based on past trends rather than actual creditworthiness. To combat bias, we need to carefully audit our data. This means checking for skewed distributions, ensuring diverse representation, and removing variables that might encode discrimination, such as race, gender, or zip codes that act as proxies for socioeconomic status. Sometimes, even variables that seem neutral can carry hidden bias. For instance, using neighborhood as a predictor in a home loan approval model might indirectly discriminate against certain racial or economic groups. Ethical data science requires not just technical skills, but also awareness of the social impact of our models. Another major issue is data privacy. When working with sensitive information, like medical records, financial histories, or personal identities, it's crucial to follow strict privacy guidelines. Regulations like GDPR, General Data Protection Regulation, in Europe, and HIPAA, Health Insurance Portability and Accountability Act, in the US place strict rules on how personal data can be collected, stored, and used. A regression model might not store names, but if it includes highly specific information, such as age, income, and location, it might still be possible to re-identify individuals, leading to privacy risks. One way to reduce privacy concerns is data anonymization, where personally identifiable information is removed before training the model. Another approach is differential privacy, which adds random noise to the data to prevent individual data points from being traced back to real people while still preserving overall trends. Beyond privacy and bias, we must also consider transparency and accountability. If a regression model is used in a high-stakes decision, like determining credit scores, hiring candidates, or setting insurance rates, who is responsible when the model makes a mistake? A black box approach, where companies refuse to explain how their models work, can lead to unfair and unchallengeable decisions. Ethical machine learning demands that models be explainable and interpretable so that individuals affected by decisions can understand and contest them if necessary. At the core of all these concerns is a fundamental principle. Just because we can predict something doesn't mean we should. Ethical regression modeling isn't just about getting high accuracy. It's about making sure our models treat people fairly, respect privacy, and can be trusted. As data scientists, analysts, and decision makers, it's our responsibility to ensure that our models don't just reflect the world as it is, but help create a fairer, more responsible future. Now that we've explored the power, pitfalls, and ethical concerns of regression, let's take a step back and bring everything together. Up next, we'll wrap up everything we've learned in a final summary so we can leave with a clear, practical understanding of how to apply linear regression responsibly and effectively. We've covered a lot of ground, and now it's time to bring everything together. Linear regression is one of the most powerful and widely used tools in data science, but as we've seen, using it effectively requires more than just fitting a straight line to data. It's about understanding the relationships between variables, ensuring the model meets key assumptions, and making sure our predictions are both accurate and ethical. At its core, regression helps us identify patterns and make data-driven predictions. We started with the basic concepts, understanding dependent and independent variables, how the regression line is calculated, and how residuals help measure accuracy. From there, we explored different types of regression, including simple, multiple, and polynomial regression, each offering different ways to model relationships in data. But building a regression model isn't just about plugging numbers into an equation. We must first check key assumptions: linearity, independence, normality, and homoscedasticity to ensure our model is valid. We also learned how to measure model performance using R-squared, adjusted R-squared, and error metrics like MSE and RMSE so we can quantify how well our model is actually working. From there, we tackled common pitfalls like overfitting, underfitting, and multicollinearity, which can distort our results and lead to unreliable predictions. We introduced regularization techniques like ridge and lasso regression to control model complexity and improve generalization. We also explored real-world applications, from predicting house prices to analyzing customer behavior, and even looked at how regression is used in finance, healthcare, and marketing. Then we took things a step further with feature selection, interaction terms, and logistic regression for classification problems. But technical accuracy isn't enough. We must also think about ethics. We discussed bias in predictive models, the importance of privacy protection, and the need for transparency in decision-making. These considerations are critical to ensuring that regression models are not only effective, but also fair and responsible. At the end of the day, regression is more than just an algorithm. It's a decision-making tool. When used correctly, it helps us understand trends, make better predictions, and drive smarter business strategies. But it also requires careful validation, constant refinement, and an awareness of its limitations. Now, as we wrap up, the real question is, how will you apply these skills? Whether you're predicting future trends, optimizing business performance, or solving real-world problems, understanding and applying regression the right way can give you a huge advantage. This is just the beginning. The more you practice, the better you'll get at building, interpreting, and improving regression models. Keep exploring, keep testing, and keep asking the right questions because data is only as powerful as the insights we draw from it.